When I first introduced the prop keyword, we were intending to also introduce a new technique with its own syntax called relational induction, where you can do induction on the proof of a proposition, which is a bit different to doing induction on data. Sadly, that feature isn't ready in time for the end of the course. So in this video, I'm going to show you a trick that's known as step indexing, which can be used as a workaround for this missing feature. And along the way, I'll show you a couple of other small features that I didn't mention before. So the idea of step indexing is that when we define a new proposition, we include some piece of data from a recursive data type as one of its parameters. And we set things up so that every time we introduce a subgoal in the prop definition, that piece of data gets smaller. So then when we're writing proofs about it, we can use proof by induction on that data type. The main example so far of a prop defined by the prop keyword has been less than or equals to on natural numbers. And we didn't notice that issue because by a fluke, numbers always get smaller in the subgoal anyway for less than or equal to. But that doesn't always happen. So sometimes we're going to need this trick. And if all else fails, sometimes we can just have an extra parameter that's just a natural number whose only job it is to count how many proof steps we had to use to prove something. Okay, so I'm going to show you an example involving state machines. So remember this state machine from the test, which had 3 states over the alphabet ABC. So I've defined those types, and I've defined a prop with 3 parameters here that says that when this machine will move from one state to another state by reading a letter. So I've given a name to each of the ways in which we can prove that the machine moves along one of these arrows. And none of these have any subgoals because these are all just kind of facts that I'm introducing. So I can write another prop that says that this machine can move along a path between 2 states after reading a string, a list of letters. And this path, this is going to be our step indexing parameter. So this guides me in how I'm going to define this prop. I should have 2 cases corresponding to the 2 things that a list can be, namely it can be the empty list or it can be head const tail. So I'm going to have, first of all, I'm going to have a way to prove that if I'm in any state and I read the empty list, I can stay in the same state, and I'm going to call this by stop. Unfortunately, I can't do this for technical reasons. Each variable is only allowed to appear once. So actually, I'm going to say prove that reading the empty list moves us from state S1 to state S2, but only if I prove as a subgoal that S1 equals S2. And by the way, don't get confused between these lowercase S1 and S2 and the capital S1 and S2. So these refer to specific states with those names, whereas these refer to any state. So the other case will be called go, and I can use it to, so I should say path, and I should use it to say that I can move from S1 after reading a string consisting of a head letter followed by a tail string to some state S2 by go. And then I will have to prove that I can step from, that's this prop that I defined before, from S1 to S2, from S1 after reading head to some other state S3, and then so I'm going via the state S3, and then I need to also prove path, that I can go by path from S3 after reading tail, which is the remainder of the string, to S2, which is where I'm going. Now here I've mentioned this new state S3 out of nowhere that didn't appear before. So I actually have to introduce this as a parameter of the proof rule go. So I'm going to say by go S3. So this is the first new thing that I want to show you, is that proof rules are allowed to have data parameters. And after I introduce a data parameter in a proof rule, I'm allowed to mention it in the subgoals. Okay. So using this, I can prove that this machine will move along some specific path. So I can say, for example, that I can move from S1, which is this one, to S2, which is this one, by reading the string A, B, B, or A cons B cons B cons empty. So I can say prove path capital S1, and then A cons B cons B cons empty S2. And the string I'm reading is a cons, so I can say by go, and now I need to say which is the state that we're visiting after reading the A. So that's S1, because we loop back to S1. So I can say by go capital S1. And now ask tells me that I have to prove that we can step from S1 to S1 by reading A, which I can do using this S1A rule. So I say by S1A. And then I have to prove that we can move from S1 again to S2 by reading the shorter string BB. So now I'm going to say by go again, and after reading B in state S1, we move to the state S2. So I'm going to say by go S2. And now I have to prove step S1B S2. That's this rule by S1B, and then that we can path from S2 to S2 reading B cons empty. So now we have another loop from S2 to S2. So I'm going to say by go S2. And I can say step S2B S2 by S2B. That's this rule. And now I have to prove that we can path from S2 to S2 reading the empty string. So for this, I have to say by stop. And by stop is supposed to have a subgoal where we would have to prove that S2 equals S2, but ask is smart enough to figure that out for itself. Okay, let's do something a bit more interesting with it. Let's prove that we can join paths together. So I want to prove that if we can path from S1 to S2 reading the string X's, and we can path from S2 to S3 reading the string Y's, and I've switched back to lowercase S1, S2, S3 here. So these are not these states, but any states. Then I can path from S1 to S3 reading the string X's concatenate Y's. So here I have, I brought the concatenate function for lists with me. Okay, so this is actually going to look quite a lot like the proof from the last video, where we proved that you can chain inequalities together. So I'm going to start by saying inductively X's, which is this list, this string here. And then I'm going to say by int I. Okay, and now, like in the last video, I'm going to, instead of saying by imp I again, I'm going to say from the thing that we've been given, which is path S1 X is S2. So now ask will case split depending on the two different ways of proving path, which I have arranged correspond to the two different things that a list can be. So we're actually really case splitting on whether X is empty or if it's head cons tail. Okay, let me just quickly tidy up the names. Yeah. Okay. Now, in the first case, we are given that x is equals empty, and ask has substituted that here in our goal. And we have also been given S1 equals S2, and that comes from this sub goal of stop, because this sub goal here corresponds to when our path S1 x's S2 has been proven using the stop rule. So now I'm going to say by imp I. Okay. Now here, we have to prove something which looks like something we're given, namely path S2 y's S3, because empty concatenate y's is y's, because if you run this program, you get y's, and S1 equals S2. So ask is able to figure out the first thing for itself, that if you run this, you get this. But the second thing, we have to give it a hint. So I'm going to do something that I haven't shown you before, which is I'm going to say from S1 equals S2. So that's this equation here. Now, back when I introduced you to from equations back in week 7, exploration 3, I told you that this wouldn't work, that from an equation would only work when we had constructors around. But actually that wasn't true. It's just, it was a feature that we didn't need back then. When you have an equation where at least one side is just a variable and you say from it, ask will actually make a substitution in the goal. So when I send this, this actually completes the proof, because this causes ask to substitute, replace this S1 here, replace this S1 here with S2, and then it recognizes this as the given that we have. Okay, so that's a bit of a new feature. We don't need this often, but occasionally this comes up. Okay, now in the other sub goal, we have a bit more work to do, but nothing as mysterious as what we just did. So here I'm going to say by imp I. And now I have to prove a path where my list is, after this program here runs, this looks like head cons, the brackets move, so head cons tail concatenate y's. And so I can use the by go rule here, which is for when I want to prove a path of a cons. And I have to name the state that the machine will move to after reading head, which I named back here. I named it S1 prime. So I'm going to say by go S1 prime. Okay, so now I have to prove that reading tail concatenate y's will move us from S1 prime to S3. And this actually looks like the conclusion of our induction hypothesis. So I'm going to say from our induction hypothesis and carefully substitute what I need. So from path S1 prime, tail S2 implies path S2 y's S3 implies path S1 prime, tail concatenate y's S3. So I've taken my induction hypothesis where x's has been replaced with tail, and I've also replaced S1 with S1 prime. And just like in the last video, this gives us, we get given an implication, and now I can say from this, and that will complete the proof, because all of my givens and my goal line up.